Okay, so good morning or afternoon or evening, depending on where you're joining us from. We're going to talk today about the transmission element reference files that come with Zygo ultraflats and ultraspheres, or with any calibrated optic that you would get from Zygo. So when you buy one of our lambda over 40 or lambda over 50 reference optics, you will receive in the box a USB stick. And on that USB stick, there will be a few files, including a DAT file, an INT, and a ZFR. There's also a couple of documents and application notes. You'll also see in the webinar, GoToWebinar interface on the right, there is a handout. That's just an updated application note that discusses everything we're going to do today, basically. So these files represent the absolute aerial calibration of your transmission optic. And what that means is we do a procedure here at Zygo that you can find some papers about on the website, where we fully calibrate the whole surface of that, and then we provide you a file that describes that surface. Now, the DAT file, which you may think is kind of what you would want to use, is really just provided as reference because we provide systems that are at a range of different camera resolutions, ranging from the Verifier 1K by 1K or 1200 by 1200 up to the Verifier HDX at 3400 by 3400. And so the DAT file really is just going to be a reference. And then the INT or the ZFR file, depending on if you're using MX or MetroPro, are what you'll use to generate your actual error correction file that you use for your specific instrument. So what we're going to do today is kind of go through turning this INT file into a usable system reference for this Verifier HD MST that I'm using today. And we can talk a little bit at the end too about other places where this transmission reference file can be useful. So to start, I'm using a 4-inch system with a 4-inch transmission flat. And that is a 4-inch ultra flat. It's a lambda over 40. And I need to begin by creating an overfilled cavity. So what that means in this case is I want to look at another flat piece of glass that's larger than 4 inches in diameter. So I'm using a 6-inch transmission flat. Really, any part that you have would be okay here. It doesn't need to be super high quality. You just want to make sure you get data across the entire aperture of your system. Now, if you are measuring with a transmission sphere and you're doing this test, you'll need to make sure that you overfill your aperture. So use a test part that is faster than your transmission sphere to make sure that you get data across your full camera. Now, I've done that. I've set up my overfilled aperture here. So I'm just going to take a measurement. And now we're going to use this measurement to determine where our camera, center of where our valid aperture is on our camera, and the size of that valid aperture in pixels. So here I've already got the Zernike view enabled and turned on. So we came to the analysis tab and we selected Zernike here. And I've changed my lateral units to pixels. So if we go back to measurement, I have laterally calibrated this system. So that's something we've walked through in some other webinars. But when I went to my Zernike view, I want these units in pixels. So if you don't see pixels, easy enough to go up to the master units here and change the lateral units to pixels. The reason I want pixels is that I'm going to use these values to generate data from that INT file. So we can open up the data generate tool in user tools. And you'll see that the order right now is set to 4. I'll set that to 12. But if I didn't set that to 12, you'll see there will quickly be an issue. So I'll leave it at 4 for now and go over to import from my USB stick the Zernike coefficients in that INT file. And they get populated up to the 4th order. Now, if you go to 12, you'll see those are blank. So we just want to make sure we set the order before we import. Now, the camera, the data file that we make should be the same size as our camera. So the width and height should be set to 2304, because if I go back to my measurement tab and look at my camera mode, I can see that's the current size of my camera. If you're not sure what the size of your camera is, you can find the camera mode control in the old MX measurement setup panel as well. Just look over there on the left and you'll see it. Now, the next thing is to disable auto size. So normally when you generate data, it will just generate out to the size of the matrix you've defined with a radius equal to half of that size. But here, I want to use the values from my Zernike measurement. So I've entered the centers here from the Zernike fit, center X and Y. And now the radius, you'll see that the value I have here from before is actually a little bit smaller. So if you look inside that application note that's linked in the handout, down on the second to last page, there's a table of clear reference apertures, or clear aperture for reference. So each reference optic, when we calibrate it, is calibrated to a specific % of the clear aperture. And I can look in that table and see that for my 4-inch, 4% ultra flat, that value is 98.4%. So what I'm going to do is just open up the Windows calculator here, take my 1106.95 pixel radius from my Zernike fit, which describes the size of my aperture for my instrument, and multiply by 0.984. That gets me 1089.24. So I'll enter that radius in here. So what we've done is basically take a measurement of a full aperture and use that to determine what is the center of our camera, where is our data centered on our camera, and what is the size of the data on the camera. So that when we generate our reference file from the Zernike coefficient, we will have a height map that is properly centered on the transmission flat in the interferometer. So now I just want to make sure I select check all, which will cause me to generate all of the Zernike terms. You're welcome to uncheck kind of the first three here, piston and tilt, which aren't going to have a big effect on how that system reference file is used. And then we'll click generate, and we'll see the data set gets created. Now, when you hit generate and that data generates, so it replaces the active data in MX. So now the active data that I have here is my generated matrix from those Zernikes. And if I view, you can see the residual is basically just floating point noise, more or less. We have created a perfect Zernike map. So now I can save data, and I'll just overwrite our ultra flat reference. And we now have a DADX file that represents the error in our transmission flat that matches our camera's resolution and is properly centered on where our data falls on this specific system's camera. So if you were to repeat this process on a different system with the same ultra flat, you would want to remake this system reference file for each system that you use the ultra flat with. So now that we've got a system reference file, we can look at how to apply it. So I just saw a question come in about, is this something to do only when we first get a new transmission flat, or should we do it regularly? So this process, you really should only need to do once for your specific system, unless something changes in the optical setup. So if service is done and a part needs to be replaced, because the transmission flat is a thick, solid hunk of glass, it should be very stable in the long term. And as long as that, as nothing in your hardware is really changing, the center location of your data shouldn't really move around. Now, there is a bit of an asterisk on that. Depending on the level of measurement you're trying to do, if you have a system, particularly a system with zoom, so either a Dynaphys type system with the 3-position zoom turret, or a verifier with the zoom that is continuous, that could change the center position. So if you're really worried about the system error file being aligned to your data at the couple pixels level, then it may be worth, you could redo this every time you change your zoom. But that's really like it's dealing with a kind of residual of a residual. So it'll be a pretty small effect. Okay, so now that we've created the system reference file, we can look at how to apply it. So there's two basic ways. One is to apply the system errors file at the measurement side of things. So I can turn on system error subtract in my measurement setup controller. And if you have older versions of MX, this will look different, but this functionality has been available for a few versions now. And if you don't have it, you'll be able to get it very soon. So we just turn on our system error subtract. Now we'll select our file that I already had there. And you can see that our camera size matches our camera. We've got our data previewed there. System error is a nice green checkbox. And if I were to take a measurement, our data now has our system error subtracted from it. One thing to note that I completely skipped is that there is an option when we're generating our file in the advanced tab to enter a lateral resolution. I would recommend doing that if you typically perform lateral calibration in order to do things like slope analysis or PSD analysis or apply filtering. That'll just make sure that you have the same lateral resolution in your reference file that you have in your data. You can see that's where that spatial sampling value comes from. So now I've applied my system reference file to my measurement. If I were to click Save Data here and save this sample measurement, that data permanently has the system reference subtracted from it. So there is kind of, in a sense, no simple way for me to open that data file, say, on another computer, and to remove the effect of subtracting the calibration file. It is, so to speak, baked in. Now, that's sometimes useful if you want to make sure that your high quality measurements are always using that subtraction. But there's times where maybe you don't want that functionality. So I'll turn off system error subtract and just take another measurement to get some fresh data here. We could subtract our system error. Go up here. Is to open the surface processing screen and go to the subtract step. So here you can just select your data file and browse to your reference, and it will then subtract that data from your measurement. And we'll even turn on an auto aperture here just to get rid of some of those edge effects. So now I'm subtracting that system reference file from my data, but if I were to save data, this always saves the raw data. So this is a raw sample measurement. And so if I were to send this file to a colleague, coworker, or a supplier or a vendor, they would not have the subtracted calibration file. They would only have the raw data. And so I would either need to send them additionally the calibration file and have them subtract it, or make sure that I save process data to capture the effect of that processing. So there's kind of two different options for how to subtract that system error based on what you prefer, what your workflow is, and how you want to handle and store your data. So that's kind of the basic run through of how to take the INT file that we provide with ultraflats and ultraspheres and to generate a DADX file that you can use to subtract the effect of your transmission element from your measurement. I did want to take a minute just to talk about some other cases. So right now I'm just measuring, basically a simple form measurement. So I'm doing wavefront error or surface form error of a plano part with a transmission flat. But there's obviously lots of other test setups that you can use with your Fizeau interferometer. So a common one is transmitted wavefront error. Now in a transmitted wavefront error setup, you typically would have a transmission flat that is aligned to a reference flat, and then you insert a plano part in between. Now in this case, you actually have the contribution of two reference elements, both the transmission flat and the reflecting flat on the other side of the cavity. So rather than using the INT file that's provided by Zygo and generating and going through this process, typically what you would do is simply to measure your cavity while it's empty, save that as a DATX file, and then to subtract that from future measurements. So in that case, you wouldn't use the transmission flat calibration file. You would simply create an in situ calibration from your empty cavity. And that's true as well for doing transmitted wavefront measurement on non-plano parts, but obviously it gets a lot more complicated when you have, for example, a transmission sphere going through a lens, which then collimates and reflects off of a reference flat. You have to be a lot more careful about, how you could apply system reference files based on, changing magnification. So that's something that I think is typically not done often, but if you had a really critical metrology application like that, I would recommend that you reach out to us and we could talk a little more about it. Now, the system I'm using here is an MST. The MST has some special capabilities in measuring multiple surfaces and multiple cavities. So one of those measurement modes is called parallel window simple. And that was historically in MetroPro considered a three-surface measurement, basically measuring a parallel window whose front and back surface both produce interference fringes. Now, in that case, in order to properly apply your system reference, you would need to use the processing sequences available for each data set. And in the three-surface case, you actually subtract your system error from both the front surface and the back surface, but not from the thickness wavefront, which is the cavity between the two surfaces of your part. And similarly, there is the parallel window transmission setup. Now, this, we'll actually get a little graphic here. This is a setup where you have a parallel part that you're measuring with a reference flat behind it. Now, in this case, you would take a measurement, you'd get results for the front surface and the back surface. For the front surface, you would subtract your system error just like normal. For the back surface, you would actually add the system error file. So because that back surface is measured relative to the reference flat. And for the optical thickness variation, you don't actually apply the system error file at all. And that's also true for the physical thickness variation. So there's some details involved in those calculations. It may be a little counterintuitive that there are certain measurement modes where you don't apply the system error, but I wanted to make sure that I at least said that so people could hear it once. And if you find yourself confused about how to deal with system error on an MST, definitely reach out. We can provide some documentation. There's also measurement methods for measuring inhomogeneity of optical surfaces. I've had this question before of, if we have this ultra flat, and how do we apply the system error when we're doing homogeneity measurements? But those measurements are specially designed, whether you're doing it on an MST or on a standard mechanical phase shifter doing the polished homogeneity test. Those measurements are designed such that if you go through the analysis, the way the software walks you through it, you actually lose the effect of your transmission flat kind of automatically. So that's a case where you don't need to apply the system error file at all as well. All right, so that's kind of the brief overview of how to take the provided INT file that comes with an ultra flat or an ultrasphere, how to generate a DATX file specific to your instrument from it, and then how to either subtract that data from your measurement acquisition or during analysis in order to apply the error file to your data to get the highest quality and the most reliable metrology. So we'll hang out for a couple minutes if anyone has any questions or other things that they would be interested in seeing. But otherwise, I'd like to thank everybody for joining me, and I'll see if we've got anything in the questions log here.
Yeah, we have one comment, question on adding the system error back in if you use the system error subtract dialog, which when you save removes the system error. Maybe you could just talk a little bit about identifying if your data set has had that system error applied by checking the attribute, and then showing how you might account for it, because we see that.
Sure. So let me just switch back to our form measurement type, and I just loaded in the data set that we took. I believe this is the one where we subtracted our system error. And what I can do here is browse to the resultant attribute selection on a plot and look at the instrument attribute for subtract system error and system error file name. And you can see that because we took this measurement with that control turned on, it's logged in the file that subtract system error was on and what the file name was. And the file name, going a little off the end there, but you can tell that would be helpful if you are in a shop where maybe you're not sure which transmission flat was used or if the right transmission flat reference file was used. And so in this case, if I wanted to kind of reverse the effect of that subtract, I could do so because I know that it was done at acquisition time by going over to analysis. And in MX 8.0, I'll open surface processing. In previous versions, you would use the data manipulate tool here. And let's just get rid of that subtract step from before. And now I would just add in an add step. So I just right click in this blank area and go to add. And I'll drag and drop that up to the top so it happens before our fit remove. And then you could just add back in your reference file right like that. And that would essentially reverse that effect. So this method of using attributes to determine if a measurement was taken in a certain way is something that's pretty useful. You can show attributes on plots like I did. There's also this attributes grid, which is displayed by default. As somebody who finds themselves doing a fair amount of forensics on data files, it's definitely a useful technique. And it's one of the nice things about the DATX file that it stores basically, the status of every control when you take that measurement. Okay, so here's another question. Are the transmission element error files valid for use in all orientations of the interferometer? So yes, they are intended for both horizontal and vertical use. The specification that we put on, so this is specifically talking about the ultra flats, which are made thicker for exactly this reason, so that when they are used in a horizontal or vertical configuration, they still meet that same specification, and you can still use your system error calibration file. All right. Anything else that you think we should cover here, Rich? Or otherwise, we will close up.
I think that's pretty good.
Okay. So thanks again, everybody, for joining me. This webinar's recording will be placed on the Zygo website and the Zygo YouTube channel. Feel free to grab that app note from the handout before you go, and have a great rest of your day.